Chapter 10, Kirchhoff's laws. After learning this chapter, you should be able to recall and apply Kirchhoff's laws. Use Kirchhoff's laws to derive the formulae for the combined resistance of two or more resistors in series and in parallel. Now we have two Kirchhoff's laws. You should know them by heart. In paper 2, they can ask you to define or state Kirchhoff's laws. And in the O-level class, you learned the formulae for combined resistance of resistors in series and in parallel. Now, here we will see how those equations are derived using Kirchhoff's laws. Then the third point, recognize that ammeters are connected in series within a circuit and therefore should have low resistance. We have learned before, you would have learned in the IGCSE or O-level classes that ammeters are connected in series with the component that we want to find the current of. So voltmeters are connected in parallel, ammeters are connected in series, and if you are connecting an ammeter in series, it should have a low resistance because it should let the current pass through it. But voltmeters have a very high resistance because when you connect it in parallel with the component, there should not be any current flow or very little current flow through the voltmeter. We want to make sure the current flows through the component that the voltmeter is connected across, but not through the voltmeter. Alright, so let's go through this part. Okay, we have Kirchhoff's first law. The sum of currents entering any point in a circuit is equal to the sum of currents leaving that same point. You have to know this definition. I have mentioned that whatever is in green boxes or highlighted in green is very important. You have to study it, you have to memorize it, because in the exam paper they can ask you to state Kirchhoff's first law, state Kirchhoff's second law. So everything that is highlighted in green in this book is very important, and also whatever is in green bold letters, that is also important. And in the back of the book, which is in the glossary, you have the meanings of these words. Okay, so if you consider a circuit, let's say there is a junction or a point in the circuit, then the total current entering that junction or that point should be equal to the total current leaving that junction or point. We call this the law of conservation of charge. Now current is the rate of flow of charge, so the total charge entering this point should be equal to the total charge leaving this point, because the time is the same. I equals Q over T. Current is equal to charge over time. The time is the same, so the total current entering this point, total charge entering this point should be equal to total charge leaving this point for the same period of time. Same thing here. So I1 should be equal to I2 plus I3. This is a junction, this is a point. This we can also call Q a point, and that's what is shown here. I1 equals I2 and I1 equals I2 plus I3 for this point Q. This equation is for point P and this equation is for point Q. So this is what Kirchhoff's first law is. The sum of currents entering any point in a circuit is equal to the sum of currents leaving that same point. Okay, then let's look at Kirchhoff's second law. There are some questions here where you have to use Kirchhoff's first law. Again, this is very simple. The total current entering this point should be equal to the total current leaving this same point. That is Kirchhoff's first law. So the current here should be 2. So it will be 7.5 minus 3. That will be the value here. Okay, 4.5. Yeah. Similarly, you can find the value of the current entering this point, and also you can find the direction. Now we can assume the direction, and if we get a negative value for the answer, that means it should be in the opposite direction that we chose. Okay, let's look at Kirchhoff's second law. Yeah, this is Kirchhoff's second law. Again, you can see it is in a green box, or we can say it's highlighted in green, which means it's very important. You have to study it, you have to memorize it, because they can ask you to state or define whatever is in these green boxes. So Kirchhoff's second law, the sum of EMFs around any loop in a circuit is equal to the sum of potential differences around the same loop. And you can see there is a loop here. The sum of EMFs, the EMF is this. We use the term EMF for power supplies. We can't say EMF of a component that is using power. For example, you don't have EMF of a resistor or a lamp. because that is using the electrical energy. We use EMF for power supplies, and we can use the term potential difference or voltage across when we consider a component. Now the Kirchhoff's second law states that the sum of EMFs, so there is only one cell here, so the sum of EMFs will be just E around any loop. Now you can see this is the loop. If you go around this, that is the loop. You can go in the direction the current is flowing. The sum of EMFs around any loop in a circuit is equal to the sum of potential differences around the same loop. That is the potential difference across this plus the potential difference across this. Now we know the Ohm's law equation, V equals IR. So the potential difference across this, we can say V1 is equal to IR1. The potential difference across this is we can say it's V2, so then it will be V2 equals IR2. You can see the same current flows through each of these resistors. So here it will be V1 equals IR1, which is what we have here, okay, using the Ohm's law equation, V equals IR. Then here the same current I flows through this because these two resistors are in series. Then here it will be again V2, the potential difference across this, V2 equals IR2. So we can also write this as E equals V1 plus V2. And if you want to write it in terms of current and resistance, then it will be this IR1 plus IR2. So that is the sum of the potential differences around that same, around the loop, around the same loop. And that's what Kirchhoff's second law states. Now this is the law of conservation of energy. The cell or battery supplies energy to the electrons, and the components here like resistors or lamps use that energy and convert it to other forms. So over here we can say the chemical energy converts to electrical or kinetic energy of the electrons, and over here what happens is that electrical or kinetic energy of the electrons is converted to thermal energy, and if it was a lamp here, it converts to light and heat energy. Okay, so the electrons or the charged particles are losing energy here and here because it's passing through a certain resistance, and over here they gain energy. So this is supplying energy, over here the electrons are losing energy. So the total energy supplied should be equal to the total energy lost or converted to other forms. That is why we call this the law of conservation of energy. And later on you will learn the definition of volt. 1 volt is 1 joule per coulomb. So that is the amount of energy given to each coulomb of charge. Okay, then again Kirchhoff's first law, this sigma means the sum of currents. Okay, sum of currents entering a point is equal to the sum of currents leaving that point. This is Kirchhoff's first law. We can write it like this. Okay, so this in sigma, it means the algebraic sum. Okay, algebraic sum or the total current entering a point is equal to the total current leaving the point. So the algebraic sum of currents at a point is 0, which means the total current entering the point is equal to total current leaving the point, same point. Alright, so that is about Kirchhoff's first law and second law. This definition is important. Again, to help you understand better, I can write it down here. I can show you the working. Now we have the circuit here. Sorry, we have the, I'll quickly sketch it. Okay, so here we have this, and then we have two resistors like this, R1 and R2. This is R1, this is R2. Then the potential difference across this is V1, across this it will be V2, and this here the EMF of the cell. So Kirchhoff's second law states that the sum of EMFs around any loop. So if you go around this loop, there is only one cell here, so the EMF will be, the total EMF will be E, should be equal to the sum of potential differences around the loop. So the sum of potential differences are only V1 plus V2. So it will be V1 plus V2. And you have already learned the Ohm's law equation, V equals IR. Now the current flowing through each resistor is I. Okay, so the same current I flows through each resistor because they are connected in series. If two components are connected in series, the same current flows through each of those components. Therefore, this will be, V1 will be, we can say V1 equals I times R1. So it will be I times R1. Now the same current flows through this resistor. So V2 we can write it as I times R2. Okay, so this is what we call Kirchhoff's second law in this example. Okay, so that's how they get this equation here. Now let's move on to the next part, and there are some more questions using Kirchhoff's first law. Here is a worked example. We will discuss this worked example now. Use Kirchhoff's laws to find the current in the circuit in figure 10.9. This is figure 10.9 over here. A circuit with two opposing batteries. Now you can see this is one battery from here all the way to here. Okay, so this is one battery, and here we have another battery, which is this one. Okay, and you can see they are connected with the negative terminal facing the negative terminal. Normally we connect cells with opposite terminals facing each other. Over here they are connected so that the same terminals are connected to each other, like here negative, negative. So this side we have positive, this side we have positive, and this is one and this is the other. So what will happen is the total EMF of this part will be the difference between the two EMF values. It will be 6 minus 2. If you connect cells in series with opposite terminals facing each other, then you add the individual EMFs. You have learned this in the IGCSE or O-level class. But if you have them facing opposite terminals, then you have to subtract. So since the same terminals are facing each other, then you have to subtract here. So the sum of EMFs will be 6 minus 2, which is 4 volts. Okay, this is a series circuit, so the current is the same all the way around the circuit. You can see they are the resistors are connected in series, so whatever current that comes out through this has to go through this and also through the two cells, or two batteries rather. A number of cells form a battery. Okay, so we can't call this a cell because of this dashed line. This dashed line indicates that there is more than one cell connected in series here with opposite terminals facing each other. Same thing for this, but this battery and this battery are connected with the same terminals facing each other. Okay, so Kirchhoff's first law states that the sum of EMFs is equal to the sum of potential differences around a loop. Now let's apply the Kirchhoff's second law to find the current. Okay, so we can call the current I, and this is the loop we have. So we are going around this. You see, it's a loop. The batteries are connected in opposite directions, so we must consider one of the EMFs as negative. And that's why we subtract. That's why we get the difference here. Now we calculate the sum of the potential differences. Again, the potential difference across this we can say is V equals IR. So V is the potential difference across this, that is I, the current I, times the resistance 10. So it will be 10I, or I times 10. And the potential difference across this will be I times 30, which is this. Now so the sum of the potential differences will be the potential difference across this plus the potential difference across this, which will be 10I plus 30I, that is 40I. Okay, so 40I is the total potential difference. The total potential difference should be equal to the total EMF. That is what Kirchhoff's second law states. Okay, for around a loop they should be the same. So we can set these two equations or quantities equal to each other. So we have 4V, okay, 4 volts is equal to 40I. Then I is equal to 4 divided by 40, which is 0.1 amperes. So the current flowing through this circuit is 0.1 amperes. Okay, then let's read the last sentence or statement here. No doubt you could have solved this problem without formally applying Kirchhoff's second law, but you will find that in more complex problems the use of these laws will help you to avoid errors. Yeah, there are other ways to do this. Okay, much easier ways you have learned, but when the circuit is complicated, you can't really use those methods, because even if you can use, you might make mistakes. Okay, so here we will actually see some examples where you are using Kirchhoff's laws. Okay, there are some more questions here which you can do. And about Kirchhoff's second law, this is Kirchhoff's second law. The sum of EMFs is equal to the sum of potential differences around a particular loop, whereas sigma E is the sum of the EMFs and sigma V is the sum of the potential differences. So here is another way of stating Kirchhoff's second law. In a similar manner to the formal statement of the first law, the second law can be written as an equation. Okay, so that's what we have. Okay, so now you understand Kirchhoff's first law and Kirchhoff's second law. Let's go through this question. Okay, here we have to apply Kirchhoff's laws, and over here you can see in this circuit we have one loop here. Okay, if you go around, or we can go this way also, and in the anti-clockwise direction. So here is one loop, and here is another loop. One loop at the top, one loop at the bottom. And also we can consider the largest loop here, which is this one. Okay, so this whole thing is also a loop. We have a loop here, we have a loop here, and we have a third loop there, which is the biggest loop. And over here we have two batteries, a 6-volt battery and a 2-volt battery. They are connected again with the same terminals facing each other. You can see positive facing positive, negative facing negative. Okay, again, okay, let's go through this. Figure shows a more complex circuit with more than one loop. Again, there are two batteries and two resistors. You can see two batteries and two resistors. The problem is to find the current in each resistor. You have to find the current in each resistor. Actually, you will get this type of question in the past papers also. I have seen these kinds of questions in your past exam papers. Okay, there are several steps in this. Worked example 2 shows how such a problem is solved. So we'll go through this one now. And you have to also be careful of the sign. Okay, the direction you take and the sign. The sign depends on the direction you consider. Let's go through that, because again some students make mistakes in the direction and sign. Caution is necessary when applying Kirchhoff's second law. You need to take account of the ways in which the sources of EMF are connected and the directions of the currents. Figure 10.12 shows one loop from a larger complicated circuit to illustrate this point. Only the components and currents in this particular are shown. Let's have a look at figure 10.2. Yeah, 10.12. Yeah, 10.12. So that is this one. This diagram here, figure here. Okay, first we will go through. Okay, we can even go through this one. So there is a loop here. Now we can consider this big loop. Okay, if you consider this big loop, then if we go around this big loop, the total EMF will be E1 plus E2 plus E. Now see, again here we have the opposite terminals facing each other, so we can add these two. But if you consider these two, see, positive terminal of this cell is facing the positive terminal of this cell. So here the positive terminals are facing each other. It's not opposite terminals, it is the same type of terminal which is facing each other, positive to positive. But here it's negative and positive. The long line is the positive terminal, the short line is the negative terminal. So here we can add the EMFs. But here when we consider this one, we have to subtract. Okay, so let's see the sum of the EMFs. Over here they have just removed the resistor. Now I will explain what this why they have like kind of like removed this rest. There should have been a component here, but if you are considering the big loop, then you don't consider the component here. That's why they have kind of like removed it. Okay, we will, when we do more questions, we will understand this better. First we'll briefly go through this one. Sum of EMFs is E1 plus E2. Now see, this is we are going to the positive terminal, so minus E3, starting with the cell of EMF E1 and working anti-clockwise. Now we are moving in the anti-clockwise direction around the loop, because E1 is pushing current clockwise. You know, the current flows from the positive terminal of the battery or positive terminal of the cell. Now these two, again positive terminal, but these two cells are pushing the current in the anti-clockwise direction. This is trying to push current in the clockwise direction around this loop. So that's why it's minus here, because E1 is pushing current anti-clockwise. So E1, E2 pushing current anti-clockwise, starting from this and working anti-clockwise around the loop, because E1 is pushing current anti-clockwise. Note that E3 is opposing the other two EMFs. Okay, that's why we have negative. Then that is the total EMF, the sum of EMFs or total of EMFs. Then we can find the total of the potential differences. So we can start from the same point and working anti-clockwise again. Okay, I will zoom this out a bit. Okay, so here we can see again we can work in the anti-clockwise direction. Now when we go this way, the current that is through this is I1. So the potential difference, again using Ohm's law equation, V equals IR, the potential difference across this resistor R1 will be I1 R1, and that's what we have here. Now we are still going down, but if you look at R2, the current from this is going the other way. Okay, so that's why we write a negative sign here. Note that the direction of the current I2 is clockwise, so the potential differences that involve I2 are negative. So it will be minus sign here, then I2 R2. That will be the potential difference across this resistor. Then across the third resistor R3, again we go in the anti-clockwise direction. Here also the current is labeled as flowing this way. So again it will be a negative sign here. So the potential difference across this will be I2 R3, using again V equals IR. So I2 R3. Then in this one, since we are going in the anti-clockwise direction, it is the same as the direction of this current through R4, which is in the anti-clockwise direction. So it will be the potential difference across this resistor R4 will be I1 R4. Note that the direction of current I2 is clockwise. So the potential differences that involve I2 are negative. I already explained this. So this will be the sum of the potential differences. This will be the sum of the EMFs for this circuit. And using Kirchhoff's second law, we can equate these two equations and find any unknowns if they have given us enough information. Okay, so we'll go back to this worked example which we were planning to do. Calculate the current in each of the resistors in the circuit shown in figure. Circuit shown in figure 10.11. Okay, so let's look at figure 10.11. that is this one. Okay, so we need to find the current, or rather current in each of the resistors in the circuit shown in figure 10.11. Okay, so again we can consider maybe the first loop, the second loop, or the third loop. It would be easier if we consider the biggest loop here. Now if you consider the biggest loop, we have to assume that there is no, this resistor is not there. Okay, so we can do it that way. Now if you consider this loop, it's only this path. This is not there in that third loop. Okay, so we take this part and we assume this is not there, and that's what they have done over here in this example. Okay, so let's go through this one. Mark the currents flowing. The diagram shows I1, I2 and I3. So this diagram already shows that I1, I2, I3. Again you can see this is the positive terminal, so this will push the current this way. Always the current flows from the positive terminal to the negative terminal outside the battery. Okay, so this will push it this way, and this will try to push the current this way. Okay, so let's say the current is coming out from here, the current is coming out from here, and then what happens here is those two currents I1 and I2 add up at point P and then pass through this wire. The current here will be I3. So I3 should be equal to I1 plus I2. That is Kirchhoff's first law. The sum of currents entering a point should be equal to the sum of currents leaving the point. So the sum of currents entering this point will be I1 and I2. The sum of currents leaving this point, which is just one value, I3. So I1 plus I2 should be equal to I3. This is the junction or the point. Okay, so that's what they have here. I1 plus I2 equals I3. Okay, let's go through this. The diagram shows I1, I2, I3. It doesn't matter if we mark these flowing in the wrong directions, as they will simply appear as negative quantities in the solution. So what they mean is, now let's say we don't actually really know the direction. Let's say maybe it's a very complicated circuit, we don't know. But if we label the direction like this, we assume it's this way. Let's say it's flowing anti-clockwise here. So we can assume it and label it. And then if we get our final answer as negative, then that means the direction we chose should be in the opposite direction. That is not correct, meaning it should be in the opposite direction. So if you label the current here anti-clockwise, meaning going this way, then here also you have to label it anti-clockwise. So you have to be consistent. Now if you label I2 going this way here anti-clockwise, here also it should be anti-clockwise. You can't label I2 here up and here also up. Okay, so if you label here up, that is meaning not anti-clockwise, clockwise. Okay, so if you label I2 going clockwise, then it should be clockwise here, and also here also it should be clockwise. Now I3 is clockwise, I2 is clockwise if you look at this loop, and if you look at this loop here, I1 is anti-clockwise, I1 again should be anti-clockwise. Okay, then choose a loop and apply Kirchhoff's second law around the upper loop this gives. Okay, so the easier one is to use the big loop, but we will consider each loop so that you have a good understanding of the whole question. Okay, so if you apply the upper loop, then you can see the total EMF in the upper loop is 6 volts. Then the potential difference here will be, now you have to, when you are considering the upper loop, you have to forget about this other loop here. So it's only this loop we are considering, because we are choose a loop and apply Kirchhoff's second law around the upper loop. We are getting this. Okay, so if you look at the upper loop, now imagine this part is not there. Okay, so it's just this that is there. So if you look at this, then the total EMF around this loop will be 6 volts, and the total potential difference will be I3 times 30, which is 30 I3 plus 10 I1. Okay, because the current flowing through this is I3, and again when you use Ohm's law equation V equals IR, the potential difference across this will be I3 times 30. So it will be 30 I3. Okay, then across this it will be 10 I1. Again using V equals IR, V is equal to I1 times R. So 10 I1. So it will be 30 I3 plus 10 I1. You can see here 30 I3 plus 10 I1. Okay, so that is equal to 6. So this is the sum of the potential differences. This is the sum of the EMFs, and only one battery is there, so the EMF will be 6.0 volts. Okay, so choose a loop and apply Kirchhoff's second law around the upper loop this gives. Okay, now we can repeat the same thing for another loop, and over here repeat step 3, which is this one, around other loops until there are the same number of equations as unknown currents. Now in order to find unknowns, the number of equations should be equal to or greater than the number of unknowns. If you have the number of equations less than the number of unknowns, then you would not be able to find the unknowns. Okay, so let's go to the second loop. Now when you are considering the second loop, you have to only assume that only this loop is there. So imagine this is removed. Okay, so this upper loop is not there. So imagine it is covered. Okay, so you can imagine like erasing all of this. So you have only the second loop now. So we will apply the Kirchhoff's second law for this second loop. So it will be, we can see the current is flowing this way. So it's up to us to choose the direction, okay, as per clockwise or anti-clockwise. So repeat step 3 around the other loops until there are the same number of equations as unknowns around the lower loop. This gives, okay, so if you look at this loop now, I can go in this anti-clockwise rather clockwise direction. Okay, then the total EMF will be 2 volts. Okay, so it's only this second loop that we are considering now. So imagine all of this top part is not there. So imagine from here to all the way here, everything here on top is erased. So we have only this part now. So it will be 2, and the potential difference across this will be I3 times 30. Okay, again we are using V equals IR. So the potential difference V across this will be I3 times the resistance V equals IR, which will be I3 times 30, which is 30 I3. So that's what we have here. 2 equals I3 times 30. Now you can see we have this equation, and this one. So we have 3 equations and 3 unknowns. The unknowns are I1, I2 and I3. So if the number of equations is equal to the number of unknowns or greater than the number of unknowns, that means we can find all of the unknowns. We now have 3 equations with 3 unknowns. The 3 currents. Solve these equations as simultaneous equations. In this case, the situation has been chosen to give simple solutions. Equation 3 gives, okay, I know in this one very easy, right? So you can find I3 is 2 divided by 30, so which is this one. So once you get I3, you can use that in this equation, substitute the I3 value in this equation and find I1. Okay, so then they get that for I1, and then once you have I1 and I3, you can find I2. So substitute the value for I1, substitute the value for I3, you will get I2. So this is I2. And you can see I2 we get a negative value, which means the direction we chose is not the correct direction. So if we chose this way and if we get a negative value, that means the I2 current is flowing in the anti-clockwise direction. It's flowing this way. Now another way of thinking how this works is, you can see the EMF of this cell is 6 volts. So this gives 6 joules of energy per coulomb. So this is giving more energy than this one. So this, is trying to push the electrons this way, this battery, but this battery is trying to push the electrons this way, and this has more energy. So it can overpower this one. So even though this is trying to push the electrons this way, because this is 6 volts and this is only 2 volts, this is a higher EMF than this, so it can push the electrons through this. Okay, so here greater EMF, so it pushes the electrons through this, even though it's trying to push this way, because this is a higher value, it can push this way, it overpowers this. Okay, so that's why the direction of I2 is in the opposite direction that they have shown here. They have shown that the I2 is in the anti-clockwise direction, but the correct direction in the clockwise direction, but the correct direction is in the anti-clockwise direction. So the I2 here should be down, here it should be up. Okay, so for I1 and I3 the values are positive, so that means the directions that were chosen for I1 and I3 are correct. Here it's down, here it's to the right. Okay, thus I2 is negative, it is in the opposite direction to the arrow shown in figure 11.11. Note that there is a third loop. Now this is what I was talking about in the beginning. This loop, which is the third loop. So if you are considering the third loop, then you have to imagine this is not there, because that is not part of the third loop. So imagine from here to here everything is erased. Okay, then you are left with this part. Okay, so that will be the third loop. So we have one loop here, first loop, this is the second loop, and then this big one is the third loop. Okay, if you consider the third loop, then the EMF will be 6 minus 2. You can see here, this is 6, this is 2, they are same poles, same terminals facing each other. So you subtract 6 minus 2 equals I1 times 10. The potential difference is V equals IR, that is I1 times 10. So it should be 6 minus 2 equals I1 times 10. However, this is not an independent equation. We could have arrived at it by subtracting equations 3 from 2. You can see here, this is equation 3, this is equation 2. So if you subtract equation 3 from 2, so that is 2 minus 3, this equation minus this one, then you would get this equation. And you can see that here 6 minus 2, that is what we have here. Then this is I3 times 30, I3 times 30. So when you subtract, this goes off, and then you get I1 times 10. Okay, so here also they have shown some example, and there are a lot of questions here, so you can do this question and even more questions. So make sure you do these questions. And I told you Kirchhoff's second law is the law of conservation of energy, because the cells or power supplies or batteries provide energy to the electrons, and the other components which have resistance like resistors, lamps, they use the energy, they convert the energy into another form such as thermal energy. So the energy supplied by the batteries to the electrons or charge carriers should be equal to the energy lost by the charge carriers when they pass through a component that has resistance or components that have resistance. Okay, so here we have the conservation of energy rule for Kirchhoff's second law. Kirchhoff's second law is a consequence of the principle of conservation of energy. If a charge, say 1 coulomb, moves around a circuit, it gains energy as it moves through each source of EMF and loses energy as it passes through each potential difference. Now we use the word potential difference for a component such as a resistor. For a power supply, we use the term EMF. So when it's EMF, that means the electrons are getting energy from the power supply. And when we consider potential difference, then that means the electrons or charge carriers are losing energy when they pass through those resistors or other components which have resistance, and loses energy as it passes through each PD. If the charge moves all the way around the circuit so that it ends up where it started, it must have the same energy at the end as at the beginning. Otherwise, we would be able to create energy from nothing simply by moving charges around circuits. So we have energy gained passing through sources of EMF is equal to energy lost passing through components with EMF. Now we earlier, when we learned about Kirchhoff's second law, we learned that the sum of EMFs is equal to the sum of potential differences around a loop. And also we can write this because when it is EMF, those power supplies are giving energy to the electron. So energy gained passing through sources of EMF is equal to energy lost passing through components with potential differences. Okay, so you should recall that an EMF involves is simply the energy gained per 1 coulomb of charge as it passes through a source. Similarly, a potential difference is the energy lost per 1 coulomb of charge as it passes through a component. Now you have to know the definitions. You should know what is EMF, what is potential difference. In the previous chapters they have explained that, so make sure you know the definitions. Alright, now we can write the equation. The work done, we know the work done is equal to energy transferred. So we can write W, which is the work done, is equal to the energy transferred. And we can also write, now we have the formula W equals VQ. Work done is the potential difference times the charge. And this is how also we can get the definition of volt by using this equation. So V is the voltage, is equal to W over Q. Okay, so the unit of voltage is volts. Okay, capital V, volts, is equal to the unit of work done, which is joule, divided by unit of charge, which is coulomb. So volt is joule per coulomb. So we can say 1 volt is equal to 1 joule per coulomb. Now remember, this is the equation with the quantities, and this is showing the units. So this is not equal to this because V is here voltage. Here this is the unit of V. Similarly, these are all units. These are the quantities. So we have this one. Now sometimes students make a common mistake when they write the equation with the a question where they have to write the units, they write the quantity and the unit mixed up together. So remember, when you are writing the definition of a unit, don't write any quantities in that definition. Meaning, don't write the symbols for any quantity. So if you say volt, volt is joule per coulomb. Volt is not work done over charge. Volt is joule per coulomb. Okay, and then this is what we have. 1 volt is 1 joule per coulomb. 1 volt is 1 joule per coulomb. And so hence we can think of Kirchhoff's second law as energy gain per coulomb around loop is equal to energy lost per coulomb around loop. Okay, I think okay, they don't have a diagram here, but anyway, we can go through this part. Okay, here is another way to think of the meaning of EMF. A 1.5 volt cell gives 1.5 joules of energy to each coulomb of charge which passes through it. Okay, I can draw a diagram to help you understand this. Let's say, use another color. Okay, let's say we have a simple circuit. Okay, we have a cell, and then we have a resistor, and let's say the EMF of this cell is 1.5 volts. So I will write here 1.5 volts. Also, you know, 1.5 volts is 1.5 joules per coulomb. So over here what the cell does is it gives 1.5 joules for each 1.5 joules of energy for each coulomb of charge. Okay, 1 coulomb of charge has a number of electrons. Okay, so it's a number of electrons here make 1 coulomb of charge. So for that number of electrons, this cell gives 1.5 joules of energy. Then what happens is when those electrons pass through this resistor, now again over here the potential difference is 1.5 volts. 1.5 volts across this resistor. This is the EMF of the cell. And the EMF of the cell, if it has no internal resistance, the EMF of the cell is equal to the potential difference across the resistor. So over here what is happening is each coulomb of charge, again 1.5 volts is 1.5 joules per coulomb. Over here when the electrons pass through the resistor, they are losing energy. So each coulomb of charge loses 1.5 joules of energy when it passes through this resistor. Okay, let's again go through this. Here is another way to think of the meaning of EMF. A 1.5 volt cell gives 1.5 joules of energy to each coulomb of charge. So you can imagine this part first. The charge then moves around the circuit, transferring the energy to components in the circuit. So when it passes, here is one component, it transfers energy. The consequence is that by driving 1 coulomb of charge around the circuit, the cell transfers 1.5 joules of energy. So over here 1.5 joules of energy is converting to thermal energy. Hence the EMF of a source simply tells us the amount of energy in joules transferred by the source in driving unit charge around a circuit. So again over here the amount of energy in joules transferred by this source in driving the unit charge, that is 1 coulomb of charge around the circuit, is 1.5 joules. Okay, so that's it for that part. Make sure you answer all these questions. Then the next part is about resistors in series. The next topic, resistor combinations. Over here we will learn how to derive the equation for the total resistance or combined resistance of resistors in series and resistors in parallel. Okay. Combined resistance is also called total resistance or equivalent resistance, also called effective resistance. So they can people can use all these different words, but it means the same thing. So combined resistance, total resistance, effective resistance, all mean the same thing. Yeah, now we will see how we get this equation. Now in the O-level class or IGCSE class also you have seen this. The total resistance of resistors connected in series is the sum of the individual resistances of those resistors connected in series. Okay, how we get it is like this. Now if resistors are connected in series, meaning the same current is flowing through each resistor, there is no other alternative path for the current to flow. If two components are connected in series, the same current flows through them because there is no other path for the current to flow. The current flowing through R1 will be I, and that same current flows through R2, which is again I. This is one resistor, here is another resistor. Now we can call the potential difference across this resistor V1, the potential difference across this resistor V2, and the sum of the potential differences here is V. So if you add this potential difference V1 and this potential difference V2, we get V, and that is what is shown here. Okay, so you can see that. Then you know, again using that equation, Ohm's law equation, V equals IR. The potential difference across the whole thing is the total resistance. Here we can call that R. Okay, the total resistance times the current. So V equals IR. So for the whole thing we can use I times R. Then for the resistor R1, the potential difference is V1. That will be equal to I times R1. Okay, so V1 equals I times R1. That's what we have here. And then V2 equals I times R2. V2 equals I times R2. And you can see it's the same current through all of them, through this as well as this. And also if you consider the total resistance of these two, you can, if you replace it with a resistor which is the same resistance, then the current again through that will be the same. So we will call that total resistance or effective resistance or combined resistance R. Then IR equals IR1 plus IR2. And if you divide the whole equation by I, the i's cancel out, and then we get this equation. So this is the equation for resistors connected in series. So it can be any number of resistors. These three dots indicate the number of, it can be any number of resistors. So the RT, the R total resistance, some textbooks use a subscript T here to indicate that it is the total resistance. The total resistance of resistors connected in series again is the sum of the resistances of the individual resistors that are connected in series. Okay, now we will see how to get the other equation, which is this one for resistors connected in parallel. To do this, we can apply Kirchhoff's first law. By the way, over here we use Kirchhoff's to take according to Kirchhoff's first law, the current in each resistor is the same. The potential difference V across the combination is equal to the sum of potential differences across the two resistors. Okay, so we use that here. Now we will go to this one, resistors in parallel. Again we are using Kirchhoff's first law, which states that the sum of currents entering a junction or point is equal to the sum of currents leaving that same point. Now these two resistors are connected in parallel because the current can flow in alternative paths here. So some current flows that way, another current flows this way. So that's why these are in parallel. And when the resistors are connected in parallel, they have the same potential difference across them. It doesn't need to be resistors. Any component that is connected in parallel will have the same potential difference across the other component that is connected in parallel with. Let's see here. So we have Kirchhoff's first law, which states that the sum of currents entering a point is equal to sum of currents leaving the point. So I equals I1 plus I2. If we apply Kirchhoff's second law to the loop that contains the two resistors, we have I1 R1 minus I2 R2 equals 0 volts. Now we have this loop. Okay, so we are applying it for that one because here there is no power source, no EMF anywhere, because no power source. So the EMF is equal to 0 because there is no source of EMF in the loop. Then the total potential difference, now here the current is going this way. Now we can consider the anti-clockwise direction. Okay, so here we can see this is going this way. So it's I2 times R2, which is this way. Then if you consider this one, minus I1 times R1. Okay, so if you move all these two terms to this side, then you will get one of the signs will be negative. So either way we can say it. Now if you consider the clockwise direction, then this will be plus I1 times R1, which is this, and then this will be in the opposite direction to the direction we are going. So then it will be minus I2 times R2. So you have to choose which direction is clockwise or anti-clockwise. Okay, so if you are using the anti-clockwise direction for a particular problem, use that anti-clockwise direction throughout the problem. And if you are using the clockwise direction, you have to use clockwise direction throughout the problem. Okay, so you can't choose, okay, this for the top loop clockwise, for this here anti-clockwise. You can't do it that way. So if you are choosing clockwise, make sure you use clockwise for the whole problem, or if you use anti-clockwise, use that anti-clockwise for the entire problem, entire question. Okay, so let's learn how to find the total resistance equation for resistors connected in parallel. Okay, this equation states that the two resistors have the same potential difference V across them. Hence, we can write the potential difference V is equal to I V over R. No, okay, V equals IR. So if we rearrange that equation, V equals IR, we make I the subject, then we get V over R. Now I1 is the current through R1 and the resistance is R1. The potential difference across R1 is equal to the potential difference across R2, and that is equal to V. So we can write I1 equals V over R1 for this resistor, and I2 equals V over R2 for this resistor using V equals IR equation, and that's what we have here. I1 equals the potential difference across the resistor R1 divided by the resistance of R1. This is the current through the resistor R1. Similarly, the current through the resistor R2, which is I2, okay, you can see here I2 is equal to the potential difference across the resistor R2, which is V, divided by the resistance of the resistor R2. And we also had this equation. Now we can substitute those into this equation. So I equals I1 plus I2. We substitute I, that is V over R. Okay, now they have cancelled out the V. Okay, so I will say, so I1 is equal to V over R. I is equal to V over R. I1 is equal to V over R1. I2 is equal to V over R2. And V is common, so you can divide the whole equation by V, and then we get 1 over R equals 1 over R1 plus 1 over R2. Now this is for two resistors, but it can be an infinite number of resistors. So if you have an infinite number of resistors, then the total resistance R is equal to 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over any number of resistances. So if you have 3 resistors, then it will be, then you will have 3 terms on this side of the equation, and this R is the total resistance. And remember, a common mistake students make is they solve this part and then they forget to take the reciprocal. Now see, this is 1 over R. This is R is not equal to 1 over R1 plus 1 over R2 plus 1 over R3. It is 1 over R, which is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So you get the value for this side of the equation, and then to find the total resistance R, you have to take the reciprocal. And then in summary, when components are connected in parallel, all have the same potential difference across their ends. Okay, you can see the potential difference across R1 is equal to the potential difference across R2. If two components are connected in parallel, then they have the same potential difference across them. So all have the same potential difference across their ends. The current is shared between them because there is an alternative path for current to flow here. So some current goes this way, some current goes this way, but the total current entering the junction should be equal to, in this case, I. So I1 plus I2 equals capital I. It's shown here, Kirchhoff's first law. We use the reciprocal formula to calculate their combined resistance. This is the reciprocal formula. And here is an example. Two 10 ohm resistors are connected in parallel. Calculate their total resistance. And we have 2 resistors. So we can use 1 over R equals 1 over R1 plus 1 over R2. On this side we have 2 terms because there are only 2 resistors. And both resistors have the same resistance. So R1 is 10, R2 is also 10. Now the denominators are the same. So these are like fractions. Therefore we can directly add the numerators. We get 2 over 10. And when we simplify this, we get 1 over 5. Now remember, 1 over R is equal to 1 over 5. So when you take the reciprocal, then R is equal to 5. Or you can also say we cross multiply. Take the R there, take the 5 there. 5 equals R, or R equals 5. Okay, or take the reciprocal of both sides. Inverting both sides is taking the reciprocal of both sides, that gives 5 ohms. Take care not to forget this step. Nor should you write 1 over r equals 1 over. Okay, so you see, this is the common mistake that students make. So here is a mistake that they're asking you not to make. Okay. You can also determine the resistance as follows. You can use this to the power -1 in your calculator and get the answer directly, because to the power -1 means 1 over that value. Okay, so 10 to the power -1 plus 10 to the power -1 and then whole thing to the power -1. So you can also use this, and that is equal to r, because already here the reciprocal is taken. Okay, then if it is 2 resistors, we can use a simpler equation, which is this one made into one equation, which is easier to solve. So we have, okay, I'll show you the derivation, because you may have to use this. And remember, you can use this if you have only 2 resistors. So I will denote the total resistance with this letter R and subscript T. RT is the total resistance, and this is for 2 resistors connected in parallel. So it will be 1 over R1 plus 1 over R2. Okay, so this is for 2 resistors connected, or we can say 2 resistors in parallel. Okay, so we have now we have to find the LCM, that is R1 R2, and then this will be R2 plus R1, and this is 1 over RT. So then RT is the reciprocal of this, so we have to invert the second fraction. That will be R1 R2 divided by R1 plus R2. Okay, so if you have 2 resistors in parallel, you can directly use this equation. For 2 resistors in parallel, the equivalent or total resistance is the product of their resistances divided by the sum of their resistances. This is the product because you're multiplying, and this is the sum because you're adding. So for 2 resistors connected in parallel, the equivalent resistance or total resistance is the product of the resistances divided by the sum of those 2 resistances. Okay, so if you use this, you can again directly get the answer. Now you can even try it for this. So it will be now here for this example, if we use it, we get here 10 into 10, 100 divided by 20. 100 divided by 20 is 5. Okay, let's move on. Now there are a lot of questions here which you can do. You must do these questions because these questions cover the theory part, the basics that you need to know in order to do the past paper or past exam paper questions. Okay, then solving problems with parallel circuits. Here are some useful ideas which may prove helpful when you are solving problems with parallel circuits or checking your answer to see whether they seem reasonable. Okay, now one more point. If resistors are connected in parallel, then the total resistance of those resistors in the parallel connection will be less than the least resistance. Okay, so again, I think you would have also learned this in the IGCSE class. Let's say you have a number of resistors connected in parallel. The total resistance of those resistors that are in parallel should be less than the least resistance of the resistor of those resistors connected in parallel. So for example, let's say you have 3 resistors connected in parallel, and that's what they mean by this. Okay, so let's say or I can even use the diagram which was here. Okay, they don't really have a diagram there. Okay, I can draw a diagram and show you. Okay, so let's say we have a number of resistors. It can be 3, 4, 5, any number of resistors, and these resistors are connected in parallel. Okay, so we have here R1, R2, and let's say we have a third resistor R3. Now the 3 resistors are connected in parallel. So the total resistance of this part RT should be less than the least resistance. Okay, so let's say R1 is 1 ohm, and let's say R3 is 1000 ohms or 1 kilo ohm, and let's say R2 is 5 ohms. So RT should be less than the resistor with the least resistance in this parallel connection. So RT is the total resistance for these resistors connected in parallel, and the total resistance of the resistors connected in parallel should be less than the least resistance. So RT, the total resistance of this part, should be less than the least resistance, which is 1 ohm. You see 1 ohm is the least resistance. So if resistors are connected in parallel, the total resistance should be less than the least resistance in that parallel connection. But if it is a series connection, this is the opposite. If resistors are connected in series, now again I can consider these three resistors, R1, R2 and R3. So R1, R2, R3. Okay, so they have the same values. Okay, so R1 is 1 ohm, R2 is 5 ohm. So the same resistors now are connected in series, and R3 is 1 kilo ohm or 1000 ohms. Okay, then the total resistance of this part should be greater than the largest resistance, which is 1 kilo ohm. Okay, so here you can understand, when resistors are connected in series, the total resistance of that series connection should be greater than the largest resistance. So it should be greater than 1 kilo ohm. Okay, so if you consider the total resistance of this part, it should be greater than the largest resistance. The largest resistance here is 1 kilo ohm. So it should be greater than 1 kilo ohm. So RT is greater than 1 kilo ohm. Not greater than or equal to, it's greater than. Here it should be less than, not less than or equal to, it should be less than the least resistance. So when it's in the parallel connection, it should be less than the total resistance, or combined resistance should be less than the least resistance in that parallel connection of resistors. When resistors are connected in series, it should be, the total resistance should be greater than the largest resistance in that series connection. Okay, so we have the equation RT, when in series we are adding the resistances. So it was what? RT equals R1 plus R2 plus R3. So for the parallel connection, RT equals R1 plus R2 plus R3, and you can understand that here we are adding the resistances. So if you look at the largest one, which is 1 kilo ohm, to this we are adding another two resistances. So that's why the total resistance should be greater than the largest resistance, because if you consider RT, we are still adding more resistances to this. So therefore the total resistance here should be greater than the largest resistance, whereas in parallel connection it will be less than the least resistance. Okay, here are some more examples. When two or more resistors are connected in parallel, their combined resistance is smaller than any of their individual resistances. For example, three resistors of 2 ohm, 3 ohm and 6 ohm connected together in parallel have a combined resistance of 1 ohm. Again, you can use the formula 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3, and then you will get a value which is 1 ohm, and you can see 1 ohm is less than the least resistance, which is 2 ohms. Okay, you can do the calculation using the formula and you will realize that it is 1 ohm, and why they have given you this example is to show that when resistors are connected in parallel, the least resistance, the total resistance should be less than the least resistance. So this is less than the smallest of the individual resistances. This comes about because by connecting the resistors in parallel, you are providing extra pathways for the current. Since the combined resistance is lower than the individual resistances, it follows that the connecting two or more resistors in parallel will increase the current drawn from a supply. Okay, so what happens is, over here the resistance will be less. When the resistance of this entire connection is less, you can get a greater current flowing through this part. Okay, so the total current will be greater because the resistance is less now when resistors are connected in parallel. And you can see here, you might have noticed this in some places. So this is the proper way to connect, but if you connect a lot of appliances like this, what will happen is a lot of appliances are connected in parallel here. Okay, so then it will reduce the total resistance and a large current can be drawn from the main supply. Okay, so you see A, that is this diagram, correct use of an electrical socket. B, here too many appliances resistance are connected in parallel. This reduces the total resistance and increases the current drawn to the point where it becomes dangerous. All right, figure 10.19, which is this, shows a hazard which can arise when electrical appliances are connected in parallel. Okay, next point. When components are connected in parallel, they all have the same potential difference across them. Okay, we learned that earlier. When components are connected in parallel, they have the same potential difference across them. This means that you can often ignore parts of the circuit which are not relevant to your calculation. Okay, so if you are given the resistance 1 ohm and maybe you want to find the current through this, if you know the potential difference across any of these components, that will be equal to the same potential difference across this, so you can find the current through this. Okay, the next point, last point here. Similarly, for resistors in parallel, you may be able to calculate the current in each one individually, then add them up to find the total current. This may be easier than working out their combined resistance using the reciprocal formula. This is illustrated in question 19. Okay, question 19 is on the next page, which is this one, and actually I think that is where the lesson ends. Okay, now what we can do is we'll go through this point a little bit. So let's say you have resistors connected in parallel like this. The current through R1, let's say, is I1. Okay, so here the current through this is, let's say, I1, and the current through this is, let's say, I2. The current through this resistor R3 is, let's say, I3. Now the potential difference across each of them is the same. We can call that V. Okay, the potential difference across R3 across R2 is also V, across R1 is also V, because they are connected in parallel. When connected in parallel, they have the same potential difference across them. Okay, so over here, what this point means is, you may be able to calculate the current in each the total current entering this point is equal to, let's say, I. Okay, so here I, and we know I the total current I is equal to I1 plus I2 plus I3. So if you know the potential difference across any one of these resistors, you can, and if you know the resistance, you can find the currents I1, I2 and I3, and then to find the total current using the Kirchhoff's law, which states that the sum of currents entering a point is equal to sum of currents leaving a point. So once you find I1, I2 and I3, simply add them, and that will be equal to I. That is Kirchhoff's first law, where the sum of currents entering a node is equal to sum of currents leaving that node or junction or point. Okay, some books use the word node for junction, especially the American textbooks. Americans use the word node for junction. The British say junction instead of node. Okay, so that is much easier than finding the total resistance here and then dividing by dividing V by that resistance, because to find this I, you can also use V equals IR. So if you are finding this I, another way to do it is I equals V over R. Now in this case, R will be R total. Okay, so the potential difference across them is V, and the total current I. So you have to imagine this whole resistance, the total resistance of this part is RT. So then to find this current entering this junction here, I, capital I, just I, that is equal to V divided by the total resistance. So here another option of doing is you find the total resistance and divide V by that total resistance to get the total current. Okay, this may be a bit more complicated than doing it this way. So here it's much easier, they say, to find I by adding the individual currents rather than finding the total resistance and then dividing the potential difference across the resistors by that total resistance. This may be easier than working out their combined resistance using the reciprocal formula. Okay, so to illustrate this, you can do question number 19. So in question number 19, you can find the individual currents across each resistor and then add them to get the total current. The potential difference across each resistor is the same. Also, you can find the total resistance and then divide it by the potential difference. You can divide the potential difference across these resistors by the total resistance to get the current. So you can do it two ways. Now if you look at question number 19, yes, that they have something like that. Okay, then you can try this. Then the last part, I don't think we missed anything here. Yes, we went through everything. Then the last part is about voltmeters and ammeters. You have to know how voltmeters are connected and how ammeters are connected. What is the use of ammeter? What is the use of a voltmeter? What is the resistance of an ammeter? Or how high or how low the resistance of an ammeter and how the resistance of a voltmeter is. Ammeters and voltmeters are connected differently in circuits. Figure 10.22. You can see this is the figure 10.22. How to connect up an ammeter and a voltmeter. Ammeter is always connected in series with the component through which you want to find the amount of current is flowing. Whereas voltmeter is connected in parallel to find the potential difference across the particular component. So voltmeter is connected in parallel or across the component, and ammeter is connected in series, because ammeter measures current, voltmeter measures the potential difference or voltage across the component. Okay, so when in series, the amount of current flowing through this is the same amount of current flowing through the ammeter. So the ammeter measures the amount of current flowing through the lamp, and this voltmeter, it measures the voltage or voltage across, okay, voltage across or potential difference of this lamp. Now the ammeter has a very low or negligible resistance, okay, because if the ammeter has a high resistance, then it will reduce the current in the circuit. Okay, so ammeter has a negligible or very low resistance. Voltmeter has a very high resistance. We don't want the current flowing through the voltmeter and going through that path. So the voltmeter has a very high resistance. So a negligible amount of current flows through the voltmeter. There is a very small current flowing through the voltmeter so that it gets activated or it gets powered. Okay, but almost all the current flows through the lamp because the voltmeter has a very high resistance, and current tries to flow through the less resistance path. Current takes the easier path rather than the high resistance. So more current flows through the less resistance path. Less current flows through the high resistance path. Ammeters and voltmeters are connected differently in circuits. Ammeters are always connected in series since they measure the current in a circuit. For this reason, an ammeter should have as low a resistance as possible so that as little energy as possible is dissipated in the ammeter itself, because greater the resistance, greater the potential difference across that, and greater the energy dissipated, or energy dissipated means converted to heat or other forms. Inserting an ammeter with a high resistance could significantly reduce the current flowing in the circuit. I already explained that. The ideal resistance of an ammeter is 0. Digital ammeters have very low resistances. Now see, this is ideal or perfect resistance of the ammeter is 0. So if it's a perfect ammeter, okay, then that means the resistance should be 0. But you know, ammeters, it's a component, so all components have some resistance. Voltmeters measure the potential difference between 2 points in the circuit. For this reason, they are connected in parallel. You can see that between 2 points in a circuit, so this point and this point. For this reason, they are connected in between 2 points, and they should have a very high resistance to take as little current as possible. That's what I explained. So they have very high resistance so that very little or almost 0 current flows through the voltmeter. The ideal resistance of a voltmeter would be infinite. So ideal, the perfect way is to have a very high or infinite resistance. In practice, voltmeters have typical resistance of about 1 mega ohm. 1 mega means 1 million ohms. A voltmeter with a resistance of 10 million ohms or 10 mega ohms measuring a potential difference of 2.5 volts will take a current of 2.5 into 10 to the power minus 7 amperes and dissipate just 0.625 microjoules of heat energy from the circuit every second. Okay, so this last sentence, you can use the formula V equals IR. Now let's say if it was this voltmeter which has a resistance of 10 million ohms or 10 mega ohms, then let's say the potential difference across these 2 points, the potential difference across the voltmeter should be the same as the potential difference across this lamp, because the two are connected in parallel. So let's say the voltmeter has a potential resistance of 10 million ohms and it gives a reading of 2.5 volts. Then using the formula V equals IR, I equals V over R. So 2.5 divided by 10 million ohms will give you this current. Can you see the current is very low? Okay, we are using that formula V equals IR. Okay, so if you want, you can also write it here. Okay, so if you use V equals IR for the voltmeter, because the voltmeter has a very high resistance, it takes a very small current. So V equals IR, then R equals V, I equals V over R. Okay, so what you have to do is substitute 2.5 for V and 10 million for R, and then what you will get is 2.5 into 10 to the power minus 7 amperes as the current flowing through the voltmeter. So you see it's a very small current. So, and if you use the formula P equals I squared R or P equals V squared over R, these two equations give the energy dissipated, V squared over R. Then you will get that the power or energy dissipated in the voltmeter is only this much. So you can use the values 2.5 if you're using this equation. 2.5 squared divided by 10 mega ohms will give you 0.625 microjoules of heat energy is used through that voltmeter every second. Okay, so this is joules. So joules is now this is the unit of heat. Okay, so if you want, now what we calculated is the power. Power is what? Joules per second. So that's why they say energy per second. The unit watt. Okay, you know the formula is what? P equals E over T. So then this will be watt equals joules per second. Okay, so that's why now what we are calculating is what 0.625 microjoules per second. So that's why they say here 0.625 microjoules of heat energy from the circuit every second. Okay, or we can say it's 0.625 microwatt or microjoules per second, because watt is joules per second. Okay, so you can see here electrical measuring instruments, an ammeter, a voltmeter, and an oscilloscope. The oscilloscope can display rapidly changing voltages. So here we have, this is an oscilloscope, this is an ammeter, because you can here see the letter A. Can you see here? There's an A there. So that means it's an ammeter. You see that A? And this is a voltmeter because we have a V there. This is an oscilloscope. So these are all electrical measuring instruments. Okay, then the last part is the summary. So make sure you answer all these questions. Now I have explained everything that you need to know in order to answer all these questions. Make sure you answer all these questions in this chapter. Summary. We have arrived at the end of the chapter, and there are also end of chapter questions which you can do. These are similar to the past paper questions. So before you answer these end of chapter questions, make sure you answer the questions that are throughout the chapter, the questions which are in the brown boxes. Okay, so that covers the theory that you need to know. After you finish that, you should be in a position to answer the end of chapter questions and also the past paper questions. But these are the very most important questions which you must answer, because it checks everything in the theory. And after you do these questions, check the answers. Okay, the answers are in the CD of the book, and if you didn't get the correct answer, try to figure out what went wrong, and if you still didn't get it, you can ask me. Okay, so let's go through the summary. Kirchhoff's first law states that the sum of the currents entering any point in a circuit is equal to the sum of the currents leaving that point. Kirchhoff's second law states that the sum of the EMFs around any loop in a circuit is equal to the sum of the potential differences around the loop. The combined resistance of resistors in series is given by the formula R equals R1 plus R2 plus R3. It goes on according to the number of resistors. And then the combined or total resistance of resistors in parallel is given by the formula, this one. Ammeters have a low resistance and are connected in series in a circuit. We learned it. Okay, it is also here in this yellow box. Voltmeters have a high resistance and are connected in parallel in a circuit. So you have to know all these points. It's extremely important. Alright, so if you have any questions, you can ask me.